Hello, Internet friends. Chris Masto here with something a little new today. Today we're going to do fuse talk. Yes, new, different, exciting, fun. Well, I'm having fun doing it. I hope you're going to have fun watching it. This is a follow up from the Mikey Pipes video that I was in about fuse testing, or really not testing at all. I want to clarify that we were just playing around with some fuses. There was nothing particularly test worthy or scientific about it. Just wanted to see what would happen if we put some different current through some fuses and how they would react. And that's what we showed in that video. But people did say in the comments in reaction to that video, well, you had a 12-volt power supply. And of course, we know that the transformer in your air conditioning system is 24 volts and it's AC, not DC. And so I would have liked to have seen what would happen if you put 3 amps of 24 volts through that fuse. Well, let's talk about that because I did respond in the comments a little bit to this point. I said that it doesn't matter. And it's an interesting question. Why doesn't it matter? I mean, first of all, is he right that it doesn't matter? What does he mean it doesn't matter? And why shouldn't it matter? Because after all, if you double the voltage, you would think you would double the power, you would double the heating of the fuse, it should blow sooner. And while that's true in a sense, you're solving the wrong problem if you're thinking about it that way. And I'm going to try to illustrate that today, first with a little bit of theory, and then we'll do a practical experiment on the bench and show how this works. So I promise you, while there's going to be some math here, it's going to be good math and short math and hopefully pleasant math. So let's just quickly define some terms here. So I want to make sure that we're only going to talk about 4 quantities. So we will use V for voltage, and in the standard way, we will use I for current, which will be measured in amps. And we will use R for resistance. And I apologize for my poor handwriting. It's a little bit hard to write on this tablet. Resistance will be measured in ohms, or that's terrible. I will use the ohm symbol for that. And then we have power. P, power, in, of course, watts. All right, and this is not going to be an electronics engineering lecture, by the way. I'm not an electronics engineer. Despite what it says in the title of that video, I have no formal training. I just play around with this stuff. But you don't have to be an electronics engineer to be familiar with V equals IR, probably the most famous equation in electrical engineering. Voltage is equal to current times resistance. And of course, you can trivially rearrange the terms and come up with I equals V over R, and R equals V over I. Just a little bit of algebra there. If you know 2 of them, you can figure out what the third is. And the other thing that we're going to use, and this is the last formula here, we only have 2 formulas, which is P equals IV. So here your power in watts is equal to current times voltage. And we could, again, derive a bunch of different versions of that, but I'm going to derive something different here instead. So we said here that V equals IR, and here we have a V, so we could just replace this V with IR. So let me back out my lines there, and we'll do exactly that, right? So we can say P equals I, and then instead of V, we'll write IR because V equals IR, which is the same as I squared R. And similarly, we won't use this one, but just for completeness, you could also say P equals V squared over R in exactly the same way by substituting the I instead of the V. So here we have sort of our fundamental math. That's the math we're going to use. So let's just go through one quick example just to make sure that we understand what we're dealing with here, right? So let's say you have 10 volts through a 2 ohm resistor. So voltage equals 10, resistance equals 2. And what is the current? Well, we have a formula right here. I equals V over R. So 10 over 2 or 5 amps. Simple enough, right? So we know our voltage, we know our resistance, we know our current, and then in this case, what would the power be? So we have a simple formula for that. P equals IV. We know I now is 5, and we know V is 10. So we can figure out that this resistor would be dissipating 50 watts, quite a bit, and it would probably go up in a puff of smoke pretty quickly. But we have this other one as well, right? So we could alternatively say P equals I squared R. In this case, I squared is 5 squared times the resistance, which is 2 ohms, or 25 times 2, and we get the same 50 watts. No surprise, because these formulas are related to each other and the quantities are balanced out such that if you pull one, you push the other, and they come out to the same answer. So multiple different ways to get the same information, but with different inputs. This will be quite relevant in just a moment when we do the actual working out with our circuit. So let's dive right into that. So let's just draw, and I apologize. Again, I am really bad at diagrams. I can't draw to save my life. So I'm going to do my best. We'll put a power supply in there. I drew a battery, and then a load here. We'll just consider that a load, but let's say that it's the coil of a contactor relay. All right, so here we've got our 12-volt power supply, and we've got our coil. In the Mikey Pipes video, we were dealing with 3 amp fuses. So let's just say, for the purpose of illustration, that I equals 3 amps. Okay, so the current through this is 3 amps. And by the way, here's an important law of electricity. In a series circuit like this, the current is the same everywhere. All right, so if you are standing here and measuring the current, you're going to see 3 amps go by. If you're standing here looking at this device, you're going to see 3 amps, and so on. This will be quite important in a few moments. Current through the whole thing is 3 amps because current through the load is 3 amps. Another important electrical law, which is Kirchhoff's voltage law, says that the sum of the voltages in a closed loop is 0. What that means in practical terms, you could think of it like this battery here, right? If we arbitrarily call one end of the battery, then the negative end, 0 volts. So we'll say this is 0 volts on this end of it, and the other end is 12 volts. That's the whole point of having a 12-volt power supply. That means that we start out at 12 volts along here, we go around this loop, and we end up at 0. So somewhere along the way, we have to have dropped the 12 volts. So if there's a plus 12 volts over here, there has to be a minus 12 volts to balance it. Now, in this case, there's only one component in this circuit, so the entire 12 volts is going to be dropped across that load. But when we have multiple components in the circuit, of course, each one of them is responsible for some portion, but they're all going to add up to 12. But in the simple case here, we know that the voltage drop across the load is 12. And so now we can figure out what is the resistance of the load. We have our formula from before. That's going to be V over I, so 12 over 3, or 4 ohms. Okay, so now let's bring the fuse into the equation here. We haven't yet dealt with the fuse, so I'm going to do my best to draw a passable fuse. That's a pretty bad fuse. So the thing that the manufacturer of the fuse controls is the resistance, because they can make that wire out of whatever material they choose and of a thickness they choose in order to create the desired resistance. And of course, they also have a melting point of the metal. So just to keep the math relatively simple, let's say that the resistance of this fuse is 0.05 ohms. All right, and now we know if the current through the load is 3 amps, then the current through the fuse is also 3 amps because the current is the same everywhere. And so you may kind of see where we're going with this now. Let's look at the voltage drop across the fuse. Now we have R and I, so we can refer to our formula V equals IR. In this case, 3 times 0.05, which is going to give us 0.15 volts. And what about the power? This is the important thing. How many watts is that fuse dissipating? That's going to affect how hot it gets and when the fuse actually blows. So we can use our P equals IV formula here very easily, since we know all of these things. 3 times 0.15, and that's going to give us 0.45 watts. So that fuse is dissipating almost half a watt, 450 milliwatts. But wait a minute, we have another way, remember? I squared R. So what we could do here as well is I squared R, which is going to be 3 squared, which is 9, times R, 0.15, and that will give us 0.45 watts. Same number. Of course it is. But the thing about this is we didn't use the voltage. And really, if you look at this entire calculation here, there's no 12. That doesn't show up anywhere in this calculation. So if we change this, instead of 12 volts, we have 24 volts, but we're still saying that our load is drawing 3 amps, then all of this math is going to be the same, right? The resistance to the fuse is the same. Current through the fuse is 3 amps. We calculate the voltage drop across the fuse. We calculate the power in 2 different ways, and we're going to end up with the same half a watt. And that's what I mean when I say that the voltage doesn't matter, because we defined the situation to not be dependent on the voltage. We said that our load is pulling 3 amps, or whatever our load is pulling, in terms of current. And because we're talking about the problem in terms of current, which makes total sense, because the reason we have a fuse is so that when these windings in this coil short out and their resistance goes down, we have, remember, I equals V over R. So when the resistance goes down, current goes up, not just through the load, but also through the fuse. And when the current goes up, the power goes up, the heat goes up, and the fuse melts. That's how they work. And you could define the behavior of the fuse in terms of the voltage drop that will cause the fuse to melt, because you know that, right? We know P equals V squared over R, the same way as P equals I squared R. But that's not very useful, because that's the voltage drop across the fuse. We don't really care about the voltage drop across the fuse in terms of its ability to protect other things in the circuit. What we care about is the current that is running through this circuit. So of course it's true that if you took this situation and you ran 100 volts through it instead of 24 volts, then yes, because you have more voltage drop across the load, the current will go up. You have more voltage dropped across the fuse. The current will go up, the power will go up, and the fuse will blow. But that's not the way these things work. You have a 24 volt power supply, or you have a 12 volt power supply, or you have a 5 volt power supply. It doesn't matter. I hope that wasn't too much theory. Let's go do the experiment now and see what it looks like. Welcome to the bench. Here's our experimental setup. It's pretty similar if you saw the Mikey Pipes fuse video. The major difference is the other day I was using a fixed 12 volt power supply because I wanted something that could put out a lot of current, and that goes up to 30 amps. In this case, I want to be able to vary the voltage, so I'm using this power supply, which has a variable voltage, but it has a maximum of 3 amps. That doesn't matter because we're only going to put 1 amp through the thing. The goal today is not to blow the fuse, it's to experiment with varying the voltage. So we'll just keep this at a steady 1 amp in order to make the math really simple. And I'm also going to use this multimeter here to measure the voltage drop across the fuse. But first, let's actually measure the resistance of the fuse, since that will play into the math. So I'm going to attach some leads to the fuse and we'll measure it with this meter. Here we go. I have a 2 amp fuse. The way it's embossed on there makes it a little difficult to see, but that is a 2. And here on our meter, we can see 0.142 ohms. That seems a bit high. And in fact, if I disconnect this fuse entirely and just short these leads together, the resistance of a dead short you would expect to be 0, but we're getting almost 0.1 ohms here. So an awful lot of that resistance we were reading before was not the fuse, it's actually these wires, these cheap thin wires, and the bad connection to the alligator clips and all of these other things are contributing resistance, and that's showing up in this measurement. Now we could do this and then we could subtract this amount from the other amount to get a better answer, or we could use a fancy feature that this meter has, which is called a 4-wire measurement. That requires some special clips, which I will attach and be right back. All right, here we are. I have attached my special 4-wire clips. As you can see, there are 4 wires going into the meter. That's why it's called a 4-wire measurement. I don't have time to talk about how this works in detail, but it's quite interesting and is related to the stuff we were just talking about. You can look it up online and see how these measurements work. It's pretty magical, and it's able to eliminate the resistance of these wires. We know that the resistance of the fuse alone is 0.03 ohms. And we can remember that in case it comes up later in the experiment. Foreshadowing. I'll get everything set up for that and be right with you. And here's our setup. Looks a little bit Frankenstein-y, but it's quite straightforward. These outer clips here are just part of the circuit that is passing the current through the fuse. And these 2 clips here are the ones that go to the meter to look at the voltage drop across that fuse. So everything is currently turned off. I have my power supply set to deliver 12 volts. Sorry about how small that is there. And I have my load set to 1 amp. So let's turn the power supply on first. So that's putting out 12 volts. There's no current going through yet because this is off. So I'll now switch on the load and we can see that it is on. The power supply is showing 1 amp. Now what's interesting here is that the load is only seeing 10.2 volts. And that is, again, because all of these crappy wires and loose connections and everything else are dropping a lot of voltage on their own, plus the fuse is dropping a little. So out of that 12 volts from the power supply, only 10.2 of that is actually going across the load, and the rest of it is losses due to other stuff. And up here we can see the voltage drop across the fuse, which is 0.028 volts, which is nearly 0.03 volts. If you remember before, the resistance of that fuse was 0.03 ohms. We've got 1 amp going through it. The reason I chose 1 is because it makes the math really easy. V equals I times R. I is 1, so V equals R. In this case, the voltage drop across the fuse is equal to the resistance of the fuse. Hey, this is Chris from the future interrupting. While I was editing this video, I realized I forgot to say one important thing. Since the current is 1 here, not only does V equal IR mean that V equals R, but also P equals IV, right? So P, the wattage, is the same as the voltage, is the same as the resistance, which means that top number there on that screen not only tells you the voltage drop across the fuse, it also tells you how hot the fuse is getting. So just keep that in mind as we watch what happens next. And of course, we're incurring some measurement losses and inaccuracy, but that's essentially why that number is what it is. Now, here's the whole point of this thing. We have our power supply set to 12 volts. So what will happen to the voltage drop across this fuse if I double the voltage of the power supply? So I can take this here, remember that's 0.028, and I can take this knob and I can turn it from 12 to 24. So we got 24 volts, still 1 amp across the load over here. And let's see what our voltage drop across the fuse is. 0.28. Interesting. I'll turn down the power supply. See what's not, well, I turned it down all the way. let's turn it up to 5 volts. See what's not changing? 5 volts, 10 volts, 12 volts. I go all the way up to the point where it won't go any higher. 32 volts maximum. Still 0.02878, almost the same to 5 decimal places. So this is what I'm talking about when I say that the voltage doesn't make a difference for testing the fuse. We could have tested it at 24 volts and 3 amps. We could have tested it at 12 volts and 3 amps. We could have tested it at 5 volts and 3 amps. The point is that if that 3 amp load is the same, then this is going to be the same. The power dissipated by the fuse is going to be the same. The amount the fuse heats up is going to be the same. And the point at which the fuse blows is going to be the same in terms of the current through it. So I hope that even if you already knew all of this stuff, you at least found that watchable. If you enjoyed it, then please do subscribe to my channel. It's a good signal that makes me incentivized to do more of these things. And I will see you in the next one. Bye.